Okay, hopefully you guys finished up that worksheet, that M40 worksheet. I'm going to do this last area function, number 10, with you here, just to recall, get the juices flowing from what we were doing yesterday. And our function, f of t, is negative 3t plus 7. So what do I know if I graph it? Well, up here at 7, I know I have a y-intercept. I have a slope of negative 3, so it's coming down kind of steep. And I'm going to make it a little bit less than that, 7. I'm going to come through just to give myself a little room to work with. And we're trying to find the area from 1 to x. And remember, x can be anywhere we want it to be. It can be to the right, it can be to the left. Okay, we don't know where it is, but we're putting it out to the right somewhere just to keep things fun and happy. And so we're finding our area function, a of x. And what we're going to do is we're going to see that's area equals 1/2 times the height times base 1 plus base 2. Okay? And I can see my height. Remember, that's always the perpendicular distance between the parallel legs, or my x-axis distance. That's going to give me x minus 1. So this is going to be 1/2 times x minus 1 times base 1 plus base 2. Well, I need to know what f of 1 is to get this height, and f of 1 is going to be negative 3 times 1 plus 7. So that's going to give me 4. And I need to know what it is here at x. So f of x is actually going to be negative 3 times x plus 7. So this side is going to be negative 3x plus 7. So when I look at this, I got 4 plus negative 3x plus 7. So that's going to be 1/2 times x minus 1 times negative 3x plus 11. And I can't really distribute that half in there very fancy at all. So I'm going to say this is going to be 1/2. And then that gives me negative 3x squared. That's 11. That's plus, that gives me 14x. And then that's minus 11. And I distribute the half. That's going to give me negative 3/2 x squared. This is my area function. Plus 7x minus 11/2. Okay? So this is negative 3 over 2x squared plus 7x minus 11/2. And as we're comparing our a of x function to our f of t function, we can see that f of t is the derivative of our a of x function. Because if we took the derivative of that negative 3 over 2 x squared plus 7x minus 11/2, we are going to get negative 3x plus 7. Okay, so the connection's still there. And so we know it's a derivative. And hopefully you guys did fill out the rest of this page. So I know this one's going to be negative 3 over 2 x squared plus 7x plus 20. And this is negative 3 over 2 x squared plus 7x minus 11/2. And the whole question of the day is, okay, our question, where the heck did this constant come from? Okay, what are we talking about? Where did all those constants come from? Well, if you paid attention yesterday, hopefully you noticed everywhere that my a value was 0. Okay, there's there. All 4 of those, none of these have a c value on them, right? It's just the algebraic part of the derivative. There's no 0. But whenever I had a lower limit other than 0, okay, notice we found out we got that c value. And the question is, where the heck did that c value come from? Okay, and it's very possible you didn't see it, you still don't see it, and that's okay. Some people had a really crafty in-person look, and they said, hey, that c value was part of the area that was missing, and I don't want to confuse anybody by that. So what we're going to do is, it's okay if you don't see the connection with it yet. That's all right. We're going to keep going. So we're just going to make a conjecture. And the conjecture is, what is the relationship between the area function a of x and the original function a of t? Well, we know a of x is sum, and I'm going to box that out, and I'm going to highlight it because it's sum antiderivative of f. Okay, what does that mean? Well, that means a prime of x actually equals f of x. Okay, a prime of f equals f of x. And notice this is a little f, okay? And I'm going to say little f. That's going to be important because we're going to be talking about big F of x and little f of x, okay? And the only difference is here, okay, t was replaced with x, okay? So that's a conjecture because we can kind of see that. We can see all of those antiderivatives were there. And we will see more when we cruise. And as I'm going along here, okay, it's important to understand what we're saying. It's some antiderivative. What do you mean it's some antiderivative? Well, we have some commands here, okay? Just like we know this is like a calculus command that tells you to take a derivative, right? This command says, hey, go take a derivative. That's what that tells us to do. ddx tells us to do that. Well, same way, this is a new command. This command tells us to find an antiderivative. It says to find an antiderivative, okay? Or the integral calculates the area. So this actually I'm going to put that in quotes. It actually calculates area, but it might not be the actual area underneath the curve because it could be positive, it could be negative, it could equal 0. Okay, it's not always going to calculate the total area, but it's going to represent some area underneath that curve. Okay, so what that does is that brings us to the next part here. So if a of x equals the integral from a to x of f of t dt, okay, all I'm doing is I'm going to be renaming, because here, this is what we found yesterday, and we calculated that, and we called it a of x, okay? All I'm doing is I'm renaming now my a of x with a big F of x plus c, okay? And what this is going to do for us right now, this is going to the capital F. First of all, the capital F is an antiderivative. And what it does is it emphasizes my c value, because this is really the value that we've been trying to find the whole time, because we're like, hey, where does that come from? Okay, so that is where our a prime of x equals d dx of f of x plus c. So all I'm doing is I'm kind of replacing a little bit in there. And what are you talking about? Because this is, remember, this is our area function. And I'm putting that in quotes, area function. But if I took the derivative of my area function, which we found out, we said, hey, that equaled a little f with an x in it, right? So if I took the derivative of my big F function or my antiderivative, it really didn't matter what that constant was, because when I took the derivative of it, it went away. In other words, what that's saying is big F, the derivative of big F actually equals little f. Okay? Big F is an antiderivative. So when I take the derivative of an antiderivative, well, what happens? Well, I get back to where I started. Okay? Kind of the same thing. Well, what happens is, if I take the derivative of my area function, I get that original function that I started with. And that's kind of what we were looking at the whole time. So that means that if I take the derivative of my antiderivative, I'm going to put my antiderivative right there. Well, what the heck does that mean? Well, that means if I take the derivative of an antiderivative, well, I get right back where I started with my x in it. That is a fundamental theorem of calculus part 1. It's kind of confusing. We're going to work more. That's not the point of today. Okay, we're going to work more with, get into that one a little bit tomorrow. But if I found my area function, okay, and it's like when I was right back here, I found my area function. And if I took the derivative of that area function, I got right back to my f of t value, okay, except my derivative of my area function equaled my original f of t, my little f function, but with an x in it. That's all I'm saying back there, okay? So if I take the derivative of my antiderivative, I get back where I started from. Okay, our question is, and we're going to come back to this, this is the fundamental theorem of calculus part 1. Our question today is part 2. Where does that constant come from? That's our question. What do you mean? What constant? What are you talking about? I'm talking about all those highlighted constants. -2, +3, -2, +2, +20, -11.5. Where are those constants coming from? Okay? So we do know that if I took the integral of from 1 to x of cosine t dt, okay, we do know that our antiderivative of this, we said yesterday in the beginning, okay, what was it? That was the sine of x plus some constant. And the question is, what the heck is that constant we're looking at? Okay, so really, I'm looking at my big F of x plus c. This is really what I'm looking at. The derivative, the integral is a capital F. It's an antiderivative with its constant, just shifted up and down. And like I say, shifted up and down, that antiderivative, excuse me, was a whole family of functions. So our question is can we predict, can we find out what that C value is? Well, absolutely we can find out that C value. Absolutely we can. And we're going to find it graphically here. And I got to hit pause because I got to fire up my calculator. And I'm going to show you. It's kind of cool. Okay, so earlier this year when we found that C value, we said that was a whole family of functions, and it was a vertical shift. It just shifted straight up and down. So what we're going to do is we're going to graph it. Now, to be a little bit more crafty here, we are going to graph it as an integral. What do you mean? I'm trying to get this thing set up here. What I mean is we're going to come here in our graph. We know that that should be a sine graph, and it should be vertically shifted somewhere. So I'm going to grab my template, and I'm going to graph my integral. Ooh, didn't want that one. I'm going to graph my template. I wanted this guy, and we're going from, where were we going? We're going from 1 to x of my cosine, right? Cosine t dt, and we're gonna graph that, and there is the graph of it. And does it look like, to me it looks like a sine wave because it looks like I could put my midpoint through here, but is it truly? So all I really need to do is I'm going to graph, okay, is that really a sine function? Well, let's graph a sine x and hit enter. Yeah, I can see that's vertically shifted, okay? So that blue one is my integral from 1 to x of cosine t dt. So it's a vertical shift. So what is that c value? Well, that c value is right here. Well, how am I going to find that? Well, I'm going to use my trace to find that, and I'm going to trace the graph, and I'm going to hit it 0. So I can see right there, I can see that shift value is negative 0.841, and I really would like some more decimals, and so I'm going to hit pause and I'm going to get more decimals on there for it. Okay, so all I did was get some more decimals in there. That shift value right there is my C value is negative 0.841471. So what I did just figure out graphically is I figured out that my C actually equals negative 0.841471. So this really, the integral of this is the sine of x plus, actually not plus, I'm going to say minus because it's negative, minus 0.841471. Yeah, I know we only have to round to 3, but that's there. And the question is, where the heck did that come from? Okay, it is a vertical shift, we can see that. So the conclusion is, what the heck is this value right here? What is that value? How did they get that? Well, if we're thinking about this, the first part, okay, is in there. And the first part right here is the algebraic antiderivative of the cosine t dt evaluated at x. So it is, the c value is actually, it's the algebraic part of the antiderivative minus the algebraic part evaluated at a. What the heck am I talking about? Well, think about this. Minus the sine of 1. What is the sine of 1? Well, if I came back here to my calculator and I added myself a page, I need a calculator page, so I don't know why I just did that. I need a 1. What the heck is the sine? The sine of 1. Make sure you are in radians. Whoa, that's kind of zoomed in there a little bit. Zoom out. What is the sine of 1? Sine of 1. It's positive 841471. That's why I subtracted it. Okay? So, as I'm looking here, what we're finding out, big F actually equals the sine function. Yeah, I'm probably losing some people, but I'll get you back. So, big F actually equals my sine function. And the antiderivative of cosine, okay, so the antiderivative of that guy is sine, and I'm finding that C value. Here's my C value, and I'm finding that in there. So what we're really looking for is this first one is big F evaluated at x minus big F at 1. Okay? Because I'm taking my 1, I'm sticking it into my algebraic portion of 1, or of the sine of 1. So where did that constant come from? Well, if I came back to here, okay, here is my algebraic portion, right? And if I put a 2 in there, what is 1/2 times 2 squared? Well, that's 1/2 times 4, that equals 2, and it's minus 2. Okay, what is this? It's 3. Well, here's my algebraic part. Well, let's put a negative 1 in there. Well, that would be minus a negative 3 plus 3. Does it work all the way down? Here's my algebraic portion. Let's put a 1 into that. That's going to be 2 times 1 squared, that gives me minus f of 2. So what we're saying is it's big F of x minus big F of 1, where I'm putting it into my algebraic part. And it works all the way down the line. So that is our second fundamental theorem. So here's my algebraic portion again. And if I plug negative 2 into that algebraic portion, well, that's going to be negative 3/2 times 2, negative 2, squared plus 7 times negative 2. Right? And it's minus that. So that's 4. So that gives me negative 6 minus 14. So that gives me the opposite of 20, which is plus 20. Woo! There it is. Same thing here. Well, if I plugged it into that, well, if I put a 1 in there, I'm going to get minus 3/2 plus 7. Well, heck, that's 14 over 2. So that's, that first one's negative, sorry. And that's my 14 over 2. So this gives me minus 11 over 2. Check it out. There's my constant. So that brings me to that portion of it. And what that really means in general, if the function f, now that's big F there, okay? If big F is an antiderivative of little f, then what this is going to equal is big F at x minus big F at a. And remember, a is a number. A is a number. So my constant is coming from my lower limit, my a value, getting evaluated. And if I continue through here, if we substitute it in b for x, meaning this is a number and this is a number, well, then I get big F evaluated at my top number minus big F at my little number, okay? And if we go all the way back and we take our t value out of the equation, no pun intended, okay, what we end up getting is the integral from a to b of f of x dx, where f is some antiderivative, and I'll talk about that some more. How I evaluate it, this is a definite integral because this is a number, this is a number. It's going to be big F at b minus big F at a. And if you're confused, remember, big F, that is an antiderivative of that guy. Okay? It's an antiderivative of little f. Okay? So, as I move along here, what are you talking about? Well, let's come back here. If I remember right, in the beginning yesterday, we did this guy with left ram, right ram, mid ram, trapezoidal, and we found also the exact area was 18, okay? So what that means is when I evaluate this, I need to find my antiderivative evaluated at 3 minus my antiderivative evaluated at 0. What are you talking about? Well, this is my little f of x in here because it is a derivative in here. And what is big F of x going to equal? Well, what is the antiderivative of that? Well, 9 is constant, so that came from a 9x minus x squared. That came from a cubic, and I need a third out in front of there, correct? So when I'm checking this out, this is big F of x. So I'm going to find big F of 3. Big F of 3 is 9 times 3 minus 1/3 times 3 cubed. Well, that's really 27 minus, what is that? 27 minus 9. 27 minus 9 is 18. And big F at 0, well, that's 0 minus 0, so that equals 0. So this is really 18 minus 0 to get my exact value of 18, okay? The only thing is, this is not the notation we would use to do this. The actual notation we're going to use, okay, it's very, I shouldn't say it's very symbolic. However, how we're going to find this is we're going to say the integral from 0 to 3 of 9 minus x squared dx equals, what does it equal? Well, what we're going to do is we're going to list our antiderivative right next to it. And then we're going to kind of put a little bracket there. Okay, and I put a bracket and we say evaluate it from 0 to 3. This is the appropriate notation. Some professors might use just a vertical line rather than that bracket. It really doesn't matter. Some people are going to put them both sides in parentheses. You're going to see I flip-flop between 2 parentheses and 1 sometimes. It's not a big deal. And then what we're going to do is we are going to evaluate our big F, because this is our big F of x right there. This is our antiderivative. And we're going to plug 3 in there. So we're going to get 9 times 3 minus 1/3 times 3 to the 3rd. And then we're going to subtract big F of 0. So this is big F of 3 minus big F of 0. And that's going to be 0 minus 0. And we get 18 minus 0. We get 18. So this is just the proper notation of it right there. And I don't need that big F stuff in there. Okay? So what we're going to do is we're going to do a few of these. And we're going to cruise right along. So as I'm moving along here, what I need to first do is this is my little f of x, okay? And I'm going to find my antiderivative. Well, that's a linear term, so that's going to come from an x squared. So the derivative of that x squared gives me my 2x plus 7x. Okay, then I got to evaluate this guy from 4 to negative 1. See, I had a few people doing this on the last test already. They're way ahead of the curve, and they were actually integrating things that you wouldn't integrate until Calculus 2 on there. What does that mean? They're using apps, and they're not being honest, and they're kind of cheating online. But so then from here, what I usually would do is I would make 2 sets of parentheses. So number 1, I would never forget to distribute that negative when I need to, and I'm just going to plug 4 in. So that's going to give me 4, and it's going to be squared plus 7 times 4. And then in this next one, it's going to take my negative 1 squared plus 7 times negative 1. And this is going to give me 16 plus 28 minus 1 minus 7, which 16 and 28, what is that, 30, 44, I hope, minus negative 6 and double negative, well, that gives me 50. So I can finally evaluate now some definite integrals without my calculator. You should be checking all these with your calculator, meaning I want you to check, type this into the calculator, make sure it outputs that. And remember, that is not necessarily the total area underneath the curve. It is some area under the curve, okay? And bottom line, we're saying this is some antiderivative, okay? It's some antiderivative. Well, what are you talking about some? Because really, I could say x squared plus 7x, because really there's that plus c in there, right? So I could say, because it's a vertical shift, I could say it's plus 10 if I wanted to. And what all that's going to do is that's going to, come on, baby, get in there. It's not going to let me do this. That's right. So let's say I did that and I evaluated it from 4 to negative 1. Well, what is that going to equal? Well, that's going to be 4 squared plus 7 times 4 plus 10 minus, that's my negative 1 squared, sorry for writing sideways, negative 1 plus 10. And it really doesn't matter what c is, because here I got a plus 10 minus another plus 10. So those constants are going to kill each other out. And there's an infinite number of antiderivatives. So I want the simplest one, so I might as well just take the one where c is 0, okay? And then evaluate my function. Well, let's roll along through here, okay? Well, what is my antiderivative of sine x dx? Well, antiderivative of cosine is negative sine, so the antiderivative of sine must be negative cosine x, okay? And I need to evaluate that from 0 to pi. And it's going to equal the opposite cosine of pi minus opposite cosine of 0, which the cosine of pi, what is the cosine of pi? That's opposite of -1 minus cosine of 0. That's going to give me opposite, this is 1, so that gives me -1. Well, this is 1 minus a -1 is +1. So that algebraically is going to be equal to 2. Okay, so the wonderful thing here, we're going to be doing lots of antiderivatives and lots of evaluating of them. Okay, so it's a good time to remember all of your derivatives and antiderivatives. So I got to come through here. I'm just going to do a couple more, and I'm going to cut this off today yet, and we're going to finish it up tomorrow. So keep this a little within reason, but all I'm going to do is, what is my antiderivative of that guy? Well, I can do it by parts, okay? Meaning by sections. Antiderivative of a quadratic, well, that's going to be a cubic. And when I take that power of 3 down, that means it has to be a third in front to turn that into a 1. Minus this is going to be what? Well, it's a linear term, so that had to come from the squared. And when I take the derivative of that x squared, well, now I get that -2 in front. And this is a constant, so that's going to be plus 3x. Derivative of 3x gives me the 3. So there's my antiderivative, and I need to evaluate that from 0 to 1. So bottom line, that's going to equal big parenthesis minus little parenthesis. This is going to be big F evaluated at 1 minus big F evaluated at 0. That is the fundamental theorem of calculus. This right here is not big, this is big F of x, not big F of 1. But okay, this is big F of x is what that is. So I get a third, 1 cubed minus 1 squared plus 3 times 1. And then that's all 0. So I just get 1/3 minus 1 plus 3. So that's 1/3 plus 2 is 2 1/3. So I could leave that as 2 1/3, or I could also call it 7/3, is how my calculator is probably going to put it out. And that is the exact area from 0 to 1. Okay? A couple more. Ooh, this is an ugly one. Remember, we're finding antiderivatives. Remember what happened when we had exponents in the denominator? Well, we typically would rewrite that little guy as the integral from -2 to -1 of 2x to the -2 dx before, okay, because we wanted to see the powers. And now everything goes backwards. Well, what is that? That's going to come from an x to the -1. And that means I need what out front? A -2 out in front of there? So when I take -1 times -2, I get that power of 2 there. And I'm going to evaluate that. But remember, it's going to be kind of tough. I want to look at that as -2 over x is really my antiderivative. And I want to evaluate that little rascal from -2 to -1, which means I plug in there and I chug it. So I get -2 over -1 minus -2 over -2. It's going to give me what? 2 minus 1. That area should give me 1 when I'm doing that. Okay? What's the next one? Okay? And I'll probably print out a big antiderivative sheet because they're integrals and we have to know. Ooh, E. When do I use E? A lot of times your limits are going to tell you what type of antiderivative is going to come out of there. And remember, this is, if I wrote that, that's going to be an x to the -1. So I might want to look at this guy as 1 to E 2 times 1 over x dx, When did I get that for a derivative? Well, we got that for a derivative out of a natural log, okay? And then I evaluate that guy from e to 1. And what do I get? So I plug it. So it's going to be 2 ln e minus 2 ln 1. And I can't leave it that way because this is really 2. The ln of e is 1 minus, leave those brackets there, yeah. 2 ln of 1 is 0. And we can finally begin to algebraically evaluate our integrals. Okay? And again, here's another one there. And bring him down a little bit. X to the 3/2 power. Well, that happens. Well, what is it? X to the, remember, antiderivative. I'm adding 1 to the exponent, so that's going to be 5/2. And I got a 1 out here, so what do I multiply 5 over 2 by to get 1? How about 2 over 3? And then we're going to take that from 4 to 1. Well, you might want to think about this guy as the square root of x to the 5th. And remember that 5th can go in or it can go out. It can be there or it can be there when I evaluate it. Okay? And most likely, looking at the numbers I have, I probs want it on the outside. So this is going to equal 2/3 square root of 4 to the 5th minus 2/3 square root 1 to the 5th. Well, that's going to give me 2/3. Square root of 4 is 2. 2 to the 5th is 32. 2/3. Square root of 1 is 1. To the 5th is 1. So this is really giving me 64/3 minus 2/3 gives me 62. Wait a minute. Hold on. River made a little boo-boo here because 5/2. This 3 down here needs to be a 5, right? So I got to come through all of these 3's because I screwed up my antiderivative. All of these 3's here, they need to be 5's, right? Hopefully you're screaming at the camera. Because now when I take 2/5 times 5/2, that gives me 1. So these are all 5's, 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 5ths, 5ths, 63/5ths. I can call it that. And if I want to get crafty, I can get crafty. See, I was kind of lazy. I always left them improper, which is perfectly okay. I never took the time, usually, to turn them into improper fractions. If you did, what would that be? 1, 2, and 3/5. Okay, either one of these or decimals if you want. Doesn't really matter. Just make sure you check them in your calculator. Okay, I'm going to do 2 more yet. I'm going to do this one, and I'm going to evaluate from 0 to 5. Okay, what's the antiderivative of 1? Well, that would be x. What's the antiderivative of cosine x? Derivative of sine is cosine, so that must be plus a sine x. And that's my big F of x. I'm going to evaluate that guy from from 0 to pi, I should say. So this is going to give me that minus that. Upper limit minus lower limit. So I'm going to take pi plus the sine of pi minus 0 plus the sine of 0. Remember trig, crazy stuff happens sometimes. So this is pi plus, what's the sine of pi? The sine of pi is 0, isn't it? Minus 0 plus the sine of 0. Sine of 0 is 0. So this whole thing should give me pi when I'm coming up, right? And the very last one, okay? Trig, my favorite. What is the antiderivative of 4 secant x tangent x? What is the derivative of secant? Or what is the derivative of secant? Derivative of secant, remember, d dx of secant x equals secant x times tangent x. So that means the antiderivative of that would be a secant x. So antiderivative of 4 secant tangent, that's going to be a 4 secant x. We're going to evaluate that guy from pi over 3 to 0. You mean I need to know my trig? Yes, you do. So that's going to be 4 secant pi over 3 minus 4 secant of 0. And what does that give me? 4. And I was always cut from the cloth of a 1, 2, square root of 3. Pi over 3 is 60 degrees, so pi over 3 is up here, which means pi over 6 is down here. The secant is the reciprocal of the cosine, so cosine would be the square root of, cosine would be 1/2. That means the secant is going to be 4 times 2 minus 4, the secant of 0. Now that's putting me right here where that's 0.10. Remember, this is the cosine. So if the cosine of 1, if the cosine of 0 is 1, that means the secant of 0 is also 1 because the reciprocal of 1 is 1. So that's going to give me a times 1. That's going to give me 8 minus 4. So that area should be 4. Okay? And from there, I'm just going to finish out number 10, 11. And we didn't do the walk this way lab, but I'm going to put a graph in there and I'm going to explain that to you tomorrow. And we're going to finish this packet up tomorrow, and we're actually going to tear into 5.4b. We're going to begin that one tomorrow. You can start your homework tonight if you want. There might be some you don't know how to do. There's a whole bunch of antiderivatives that you're going to need to know, recall, and memorize, and you need them quick. Remember, every derivative we learned has an antiderivative. Even the inverse sine, inverse cosine, inverse tangent. We need to know them all. So we're going to practice them out. I'm going to post a sheet either one of these days on It's Learning that shows you all these that you need to memorize so you know. If you remember your derivatives, you will remember your integrals. Hey, I hope I cleared up a little confusion if anybody was confused. I enjoyed playing math with you once again today. And all I ask is you do the best you can. Have a good day. Talk to you tomorrow.